Hope you guys are doing well. Um, I have got few requests on Verilog coding. Um, I would like to discuss a simple FIFO example, and we're going to be coding a little bit and discuss about the good coding styles. All right. So you may be aware of the FIFO operations. You might have studied in before, or even though if you have not studied, you're watching my lecture first time. It's a simple operation. So data comes in um, through one end, first in, and goes first out. Okay, and we have to keep track of the read and the write, because read and write can happen. You may have at different time read is happening and different time write is happening. um, Now in this example, I'm assuming that we are working on one clock. Read and write is happening on the same clock. However, the when to read and when to write, they may be different. That's why we need a FIFO, that you have some data to be written to FIFO. You write um, and increment the write pointer. And then when you read, you increment the read pointer. Okay. So initially, you're in this example, let's say I have 4 entries, 0, 1 to 3. Initially, your read and write pointers are 0, 0, and we say, FIFO is empty. There is nothing here in the FIFO. Okay. Now, as the data or entries are written, the FIFO pointers are incremented. So for the condition, when the FIFO is empty, you have read pointer is equal to write pointer. But this equation will need to change, right? You can have FIFO full as well when these pointers are equal. We'll discuss it later, okay? But for the empty condition, this is sufficient. When both pointers are equal, you have the FIFO empty. Now, as you are writing the entries into the FIFO, you are incrementing the pointers. Okay, good. Now, what happens when you reach the last entry? And when you increment the right pointer, it will wrap around. Okay, and when it will wrap around, then also FIFO is full. So how do we handle this situation? Okay, so what if we have one extra bit? Okay, you can call it a MSB of the read and write pointer, one extra bit to indicate the wrapping around operation, or some people may call it the direction when it is going full or empty, whatever way you want to refer to, but just one simple extra bit. Okay, so this pointer rolls over and this one extra bit is set to 1. So now you're getting the idea that even though when the wrapping around is happening, read pointer and write pointers are equal, but that the MSB bit is not equal. So that is the condition for the full. But if these two are equal, then we have the FIFO is empty. Okay. So we arrive at the condition when the FIFO is full, that read pointer 1 down to 0, that can represent 4 location, equal to write pointer. So 0, 0 equal to 0, 0, and the MSB bit, okay, they should not be equal. So I'm using the XOR operation, or you can use just not equal, either way. Good. So that is the condition for the full. Now, when we come to the design, so remember when you are designing or writing a Verilog code or VHDL code to develop a hardware circuit, think about the schematic in mind first. That's very important. And then think about what are the inputs and outputs of your block. So in this simple example, what would be the inputs to the FIFO? Well, we have the read enable. Okay, when do we read? Write enable when we write to the FIFO. We have the clock, we have the reset, and we have the data. Now this data can be of complex data type, um, right, or a simple logic type, um, right. You can arrange your data into structures and then feed the whole structure in the FIFO. All right. So those are coding techniques, right? High-level coding techniques. And what would be the simple outputs of the FIFO? FIFO is status. Either FIFO is full or either FIFO is empty. Okay. Or so either full, either empty, or we have the entry in the FIFO. So FIFO is neither full, neither empty. Okay. And then we give the data out, read data out from the FIFO. All right. Now let's think about what we need in terms of the logic. So we definitively need to store the read and write pointers. Okay, that will tell the location, okay, of the entry to be fetched or read, and location where the entry to be written. So we definitely need the flops to store the pointers, and also we need the memory. Now the memory can be of just simple register array, or a physical memory which you may instantiate in your code. Okay, and then few logic gates or combinatorial logic you need. All right. Okay, so having that frame in, a slightly schematic picture in mind, that will help in terms of writing a optimized Verilog code. Now let's look at an example um, of a Verilog code of this simple FIFO. So I'm going to be writing a simple FIFO example code. Let's call it hrfifo.svh and hrfifo.sv. So two files. One is the header file and one is the actual Verilog file. It's a good idea to have two file structure. You can have multiple files. I prefer to use defines and parameters or structures in a package, and that package I keep it in the SVH file, and the actual Verilog code is in the SV file. It totally depends on you how you want to structure. Okay, so let's put some comment, copyright, my name initial, my channel name. Okay, so let's call it package okay. Now let's put okay, so this is actual syntax and all you can check as I'm writing this code. Of course, it's not simulated. So this idea to write the code is to give you an overview and sort of, or explain a little bit about the coding techniques. Okay, so let's define the structure. So we define a packed type of a structure. You can have packed and unpacked. Packed kind of structures are typically used, and they are good for synthesis tools. And it's like packed structures are like a packed array of the bits. Means you don't have any empty space in between the bits. You can think of that way. So we prefer to use packed structures for grouping the signals. Now, in terms of the FIFO, so let's say F in, or let me call it F enables. that is a better word, all the enables. Okay, FIFO enables. Now we can have read enable. Okay, or we can have a write enable. Okay, let's call it a short name, FIFO enable, read enable, and write enable. All right. What else we can group here? So this is a control. Think about keeping your structure grouping, like control variable separate and the data variable separate. Okay, so we have FIFO controls here, and then let's group the clock and reset together. Think about clock and reset are routed together. You can have some flops on clock A, some flops on clock B, but then the reset which is going to the clock A flop may be different. So it's a good idea to keep clock and reset together. Um, F fact. Let's call it a clock reset. Let's go type T. Okay. And let's call it logic clock. And typically reset is active low we use. If you are using active high reset, you don't put underscore n. Underscore n is a convention of active low reset, and I'm using this reset as async reset. So however, the deassertion is synchronized with clock. So see why I was saying that keep the reset and clock together, because we want to make sure that the reset going to our flops is synchronized with respect to the clock. Okay. When you are working on a module level, you don't worry about the synchronization, because synchronization may happen outside of your smaller module. But keep in mind that the reset needs to be synchronized, especially the deassertion is synchronized with the clock. Okay. Now, what do we need as an output? Okay, which means either you can call it a response or status. FIFO status is a better word. Now, you can have, different kind of status coming out of the FIFO. More common is full, indication of when the FIFO is full. And when the FIFO is empty. You can also create logic for overflow or overrun. Underrun. You can also have, let's say, you can send how many entries are in the FIFO, right? If you want to. But let's call it, let's say, full and empty condition first, right? And that's good. So that's good. Now let me okay. 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 Now, so I saved this file. Now let's type the code. Okay. The actual FIFO code. All right. So we got to include this SVH file which we have just created. Also, I forgot to put one thing. Usually I prefer to put some sort of a if-daf so that um, if end of then define this helps in let's say if you have multiple files uh, and you are compiling, then it won't complain, but I mean depending upon the compilation tool, but usually I prefer to put some defines in the header file. Now let's write the code now. So module char FIFO, and we want to have some parameters depth of the FIFO, let's call it 4. So let me put here, that's good. Let's call it 4. Next parameter, call it the width, or let's call it data type. So we want to put logic parameter type of d type equal to, let me call it just logic 1 down to 0, or so that's just telling me that I can feed any type, right? I can parameterize the type which is going to the FIFO. Okay. What else I want to keep? Width, data width is parameter. Let's call it data width is 2, 1 down to 0. Okay. And we can add parameters more later on. And module. So we have created a shell. Now, after creating the shell, what I'm going to be using, putting the code in. Okay, now, so let's say, what are my inputs? Input, I have created the type f enable underscore t f en underscore I. So these are the enable underscore I is the FIFO enables, that is a read or write. Then I have the input dtype data type, okay, and then data underscore I, okay. That data is written to the FIFO of the type T type. Okay, now I also need to input clock reset underscore T, let's call it CR, okay, and then output T type, that is the data output from the FIFO on read, and also I need to output status, okay. Okay, so after, so now you see how compact your interface becomes. You have properly structured or grouped the wires together. We have the enables, we have the data out, and we have the FIFO status. All right, good. Now let's keep our local signals on the top, and okay, and then let's put a register section here. We're gonna keep all our registers, okay, and then this section bottom for module instances. Okay, and so we have the module instances at the bottom. We have registers. After registers, I typically like to put outputs, module outputs, and usually I prefer flopped outputs. They help in timing later on in the placement and routing stage. So all of the outputs, I say assigns status underscore O is equal to, I'm gonna create a wire or not single wire but group of signals called status underscore flip-flop, so flopped version of the status feeding to the output, okay, and then I would have to feed data underscore O, and then that goes to data. Now data we're going to be storing in the register array, and then we're going to be fetching the register array. Now if you have the memory, you can instantiate the memory, okay. So let's say if you have memory here, I put a note, and use it. For example, let's say you have memory, and that, right, you can have its parameters, you can instantiate here. But in this example, I'm just gonna assume local memory, which means that gonna have D-type registers, let's call it register memory, and depth -1 down to 0. Okay. Now the depth, we have to get the bits, so let's say depth W, which means that So that will give me what is the depth of the FIFO based on log 2, how many bits, -1 down to 0. And this is of type D type. So D type signal I have declared here, and whatever is the D type I have here. Okay. Now, having said that, I want to put some, complex type here for the data. Okay. So you can call it structure packed data type underscore T, and that is F5O data. So you can have in this FIFO data, let's say 15 down to 0 D. You can also have some kind of a pointer where this data is stored. Let's say you are fetching the data from the linked list. Okay, so you have the pointer, you have the data, and that whole thing you want to put in the FIFO. So you can create a complex data type here, and then when you will instantiate this, you can feed this complex data type to the FIFO, and that will be good to go. Okay. All right. Okay. Now let's define. Remember we need to define our pointer, and we also need to define a W pointer. Now here you got to find the how many bit wide would be these pointers. Okay, remember we said that we want to keep one extra bit. Okay, so let's say we want to keep one extra bit for the read pointer and the write pointer. So depth down to 0. So here the memory goes from the CLOG to depth -1. Okay, and your logic pointer is going to have the same, let's say -1 plus 1, if you want to keep the same consistency with this. So whatever is here, register memory is going from, let's say, 0 to 10. So it's going to go from 0 to 10 plus 1 down to 0. Okay, same thing here. We have one extra bit for the read and write pointer. Okay. Now, what do we also need? The status. Okay, let's define the status. Let's say dwire of the flop is the Q output. So we define here same way, read pointer D input of the flop, read pointer of Q output of the flop. Okay, what else we need? So we have the status, we have memory we have, and we have to define the data type. Okay, so then data. Okay, now I'm not calling here flip-flop. I don't have to register the data because it's already coming from the register array. So we just directly feed the data out to the output. Okay, rather than feeding the flop towards them. Now, in order to create the registers, I prefer to use a define. Okay, this define or macros, Verilog macros are very helpful. Okay, define, let's say flip-flop with a reset. That means the Q output, D input, clock reset, and the reset value. Okay, this is the define for the flop. So what we can say here is that the Q output always FF, okay, at the rate CR dot clock pause edge CR dot clock neg edge underscore N Q output is equal to now if we have reset, then we feed the reset val, and this is the active low reset, right? That's why we have inverted resetting logically. Otherwise we feed the D value. Okay, you could also have another template or macro for flip-flop which doesn't explicitly have the reset connection. So let's say Q D CR. So in this, you don't explicitly say reset value. These flops are smaller in sizes. The flops at line number what's the difference in the flops at line number 32 and 33? 33 will lead to smaller flop size than 32. The reason how the physical layout of these two flip-flops is. In 32, you have explicit reset val defined. In 33, you don't have the explicitly reset value defined, but this flop also will get the reset. Okay, so that reset will get from the common reset defined at the chip level. Reset value will be default 0 or 1, whatever is set at the physical design. The smaller cell sizes, line number 33, that's the key difference. 32, a little bit bigger. I prefer to use line number 33 flops for data path, where I just need to store and feed the data. I'm not worried about the reset value. 32 I prefer to use for the state flop or flip-flops for the state machines, but nevertheless you are feel free to use either of the one. I sometimes use either way, but definitely for the flops which I need to reset, especially FSM flops, I prefer 32. Okay, this is just me. So we have registers, so let's use this define macro, and how easy it is to create registers. So you define once and you just keep using the template. You don't have to write again and again too many lines like always FF. So here we wanted to create F status flops. This flop output status CR, and the reset value is 0. Okay, and then what else flop we needed to create? Read pointer and write pointer. Okay, so now here WPTR looks like I have a typo here. Okay, and similarly we can create for the read pointer. All right, so we have our registers flip-flop we have defined. we have also defined okay, memory. So let's initialize. You want to initialize the memory or register array, or you don't want to, it's totally up to you. So resmem, okay, and then now let's put some combinatorial logic here. Combinatorial logic, or in other words, we are creating um, the D input of the flops, for example, or some other combinatorial logic. So for example, we need to get the when the FIFO will get updated. Okay, so always com, and we have the so let's say data, we have declared the data, and the always com data is equal to that actually not needed. So let's say here resmem rptr underscore ff. So whatever is the entry, okay, and that data is of D type, at the read pointer flop, we're gonna feed to the data, okay, and then the data is sent to the data out. Now, when to update the entry in the resmem, okay, or in other words, when to write, okay, resmem wptr underscore ff, we're going to be writing to the memory the data I, if, now the conditions, okay, so we have enable underscore I dot w. See, we have defined the enable wire up, and then the enable structure has read and write. So we are saying here that the write enable is there, and FIFO is not full, okay. So FIFO is not full, which means that the status flip-flop dot full, these two conditions need to be true. If these two conditions are true, then we will write whatever is the data input to the memory, okay. Otherwise, we just keep whatever is data in the memory. We don't update it. All right. On line number 35, I made a mistake. So we read the data when the read enable is there. Then only we read the data from the memory. Otherwise, whatever is the what will be on the data. Say when the read enable is not high, uh, uh, what would you send? Okay. Whatever is the input data or on the data bus, you just send out if the read enable is not high. the read enable is high, then we send whatever is on the read pointer. Okay, so we have done that. Now let's update the pointers, because we got to update the pointers. Now here we forgot one thing, that our depth is one less of the bit. So here we need to get uh, zero. That will be the correct one. And then similarly here we got to change, because here what we are doing is right pointer FF, and where's mem. Okay, so that is the one. Depth of the FIFO -1 down to 0. Okay. Please note that there may be syntax errors, so please feel free to correct syntax error in your code. My intention is to explain the logic and the flow of the code. Okay, don't um, um, don't count me on that. I'm writing the very syntax-free code, but I'm just live writing for you, so there might be expected syntax errors. But the idea, you got it right. So the pointer right, read pointer right pointer width, we got to have one extra bit. Okay, and now so we created the output data. Okay, and we have put the data in to the memory. Now we got to update pointers. We got to update the read pointer when enable underscore I dot read is high, then we increase the pointer, otherwise we stay where we are. Okay, here we have to have one more condition, that if the FIFO is not empty. Because if the FIFO is empty, you're not increasing the read pointer. Okay. Similarly, if the right pointer, okay, if the right pointer, you're gonna be increasing only when the right enable is high and the FIFO status is not full. Okay, now tricky part is to have a full and empty condition. Okay, so when the FIFO will be full. So as we said, FIFO is gonna be full when RPTR FF depth that condition along with MSB bit condition. Okay. Let's call it XOR. So when these conditions are satisfied, then only the FIFO status will be full. Okay, which means our pointer FF -1 down to 0. Okay. Zero. Okay. So we have 1 down to 0 and read pointer MSB bit. Okay. Which means what would be your MSB bit? See. That is the MSB bit, right? XOR which means that one bit less or actual depth up to let's say 4, then you go from 2 down to 0. Okay, for example 4D FIFO will have pointer width, will have address from 00, address goes from 2 down to 0, and MSB is bit 3, so PTR width will become 3 down to 0. Okay, so the condition full becomes PTR 2 down to 0 equal to 2 down to 0 and three XOR 3. You got it? And similarly, empty condition, when read pointer so this is simple. When both pointers are equal, then only we would call FIFO is empty. Good. Now, 5 pointers will roll over, and because we have the one extra bit to set, then MSB to take the decision when it is full or when it is not full. Now, here, now these pointers are rolling over, and we have taken care of where to write in the memory up to depth -1 down to 0. So when these will roll over, right, that will take care of. Okay, so this is so we covered the status wire. The status wire or feed into the the input of the flop, and we get the status FF. Similarly, we have W pointer flop, read pointer flop, and the data which goes out from the memory is when the enable is high for the read, and whatever is in the memory at that location, a read pointer uh, at the time feed it to the data, and the data is fed to the outputs. All right, so now let's this completes the FIFO. Okay, so as you can see here, we did the defines for the package, and then in the package we put the common elements for, we group the common signals into structures, and the idea to keep common signals is based on control and the data. So group the control wires together and the data wires together, and keep the difference between the input and output. So here we have the enable, which are control wires at the input, we keep in one structure. We have control wires, not control wires, they are global wires. Clock and reset are global wires. Inputs, we keep it in one structure. And then we have the status. We have the status output, status control wires, we keep it one structure. We do macros defined for common elements such as flip-flops, AND gate, NAND gate, NOR gate, and that you can have a complex design here for the FIFO. But for this lecture, this simple design is good enough. So I hope that you guys have this lecture is helpful to you. And also one thing to note, that I try to keep combinatorial logic separate in separate sections of the file, flip-flops or registers in separate sections of the file, outputs in separate sections of the file, and module instances in separate sections of the file. That way, when your file gets bigger, it's easy to manage, and your all local signals parameters are defined in the very beginning, so that you don't have to worry about compiler errors and all. Oh, I can't find this signal, this is not defined at all. So keep it at the very top, and then you keep using them and group the signals into structures. Very good. So having said that, I have put a few of the code guidelines as I said earlier, use structures and also follow some conventions. Like I had used _I for inputs and _O for outputs. That is very helpful to quickly know, in thousands of signals, oh, this is my primary output of the module, this is my primary input of the module. _I, _O is normally used. You can use as a suffix or you can use as a prefix. I prefer to use suffix. It's totally up to you. This line number 30 is very important, that think about the schematic before writing the code. Many people, they just jump onto the code like C programming or any procedural programming languages, but that is very bad style. Its hardware is different. If you don't have the schematic image in your mind, it will be very difficult for you to write an optimized code. And many people, new designers, they end up writing a behavioral code which may not well synthesize. So be very careful, okay? And practice it, then you will write a very, very well optimized code. For FSMs, important for FSMs, keep your combinatorial logic and sequential logic in separate blocks. Let's say always com block for combinatorial logic, and always you have registers, your flip-flops. Use the defines for defining those flops. use packages for common parameters, define structures, um, use define macros, Verilog macros for common elements. And last but not least, write a very clean code uh, and use comments, right? Write comments, enough comments in your code. Think about uh, tomorrow somebody else need to manage that code. So if somebody else need to manage that code, uh, it is very helpful if you have lots of comments and information. uh, it just nice of you to have a lot of comments. um, it is just helping the other person um, who will be maintaining your code tomorrow. Thank you so much for listening. I hope I made sense in this lecture. I know many of you who are watching my lectures are already expert. So please excuse me for my syntax errors or mistakes in the lecture. My intention is to help you guys. Thank you very much. Have a wonderful day. And please do like, subscribe, and share. I noticed that Google is not showing my lectures. Looks like the viewer count or the time viewers have been watching is being reduced. So please help watch more and share more. Thank you. Bye.